Hello students, today we will discuss the second part of the Crank-Nicholson scheme. Let us discuss it. Let me quickly show you what is different today. First, look at this scheme. Now, you can see here that we are using a scheme with the help of which we will write here on the right hand side the time step at j minus 1, and with the help of the time step at j, right? So the j minus 1 as the approximation using the information at j, which is of course implicit, right? And the rest of the formula is about the centered, right? Centered in space and backward in time. Now, what is special about the new method? Let us go to the new method. Okay. Now, what is happening in the new method? We are saying Crank-Nicholson at j plus 1 and j averaged. So now what is meant by this? So now let us read it. Combines the stability of an implicit method with the accuracy of a method that is second order in both space and time. Simply from the average of the explicit and implicit forward in time, centered in space, FTCS schemes, left and right hand side are centered at time step j plus half. Now let us understand it in depth. Let us look at the left hand side, which is quite straightforward. N is the index for space, j is the index for time. J plus 1 to j means that you are saying forward in time. Now here I have the capital D. Now here I have delta T. Here I have delta X square. Here I have 2. So I will merge everything in the form of a coefficient. Okay. And I'm going to call it alpha in future. Now let us go inside the bracket. There are two terms written, the first term and the second term. The main difference between these two formula is that this is the centered scheme in space, but at the j plus 1th point, and this is the centered scheme in space, but at the jth time location. Now, if I say that take the average of j and j plus 1th time step, finite difference scheme for space. Actually, I am talking about something in the middle of j plus 1 and j. So that is actually j plus half time step, right? So this is why, that is why we call it j plus half time step. But in writing, we will write the centered scheme for space at the j plus 1th point, centered scheme for space at the jth point, and divided by 2. So this is now the average. All right. Now, how we are going to write it in the matrix form, and that is very, very important. So please learn very carefully today's lecture. This is the scheme. Then I will write it in the matrix form, and then I will write it in the compact matrix form. Okay. Now, what is happening here? You have here you have here this side, right? What is written on the left hand side? Left hand side, you have simplified everything from this scheme, and you had an idea in mind. What was the idea? The idea was to take all the j values on one side, all the j plus 1 values on the other side, right? And here you can see that all the terms with the j index are on the left hand side. All the terms with the j plus 1 index are on the right hand side. Okay, now the coefficients are alpha, 2 minus 2 alpha, alpha, minus alpha, 2 plus 2 alpha, and minus alpha. Please make a note of these coefficients because these will make the diagonals tridiagonals of the matrices, and these will also be written in the M file. Okay, so keep this in mind. Right now, what is happening here, students? We can write it in the matrix form. And another important thing is that how many times, for example, let us say that J is fixed and we are varying N. So from what to what? So we are saying that if I have a rod and I want to find the temperature at N plus 1 points of that rod, but the point is that 0th temperature and N plus 1th temperature is given. So how many are left? Let's say 0th and nth are given, then how many are left? So you will go from 1 to N minus 1. Okay, so because the boundaries are given to you. So start substituting N is equal to 1, 2, 3 up to so on to N minus 2 to N minus 1 in this scheme on your notebook. Okay, and please put your video on pause and start substituting the values for N in this scheme and tell me what you get. So the Crank-Nicholson method can be written in a matrix form as this. For example, let us substitute N is equal to 1 in this scheme. What will happen? Let us talk about the right hand side. What is going to happen? N is equal to 1 means 0 index here and 1 index here and 2 index here, right? So what are you going to do now, students? Just as we did in the classroom, you will first make a vector and then you will make the rows here in this matrix. By now you must be an expert in doing this because we did it in the previous lecture and then we did it in the classroom. So you are going to select the coefficients and you will write it here row wise. Okay, and you will see that when you again multiply the matrix with this vector, you should get back the system of equations. For example, how many equations are you expecting now? N minus 1 equations, right? But the point is that the order of this matrix, the order of this matrix and the order of this vector are different, and the number of rows and the number of columns in this matrix are different as well. How? Because you are going to substitute N for 1 till N minus 1. So for example, capital N is 10. So 1 till 9 means you are expecting 9 equations. But the point is that there is a condition at the 0th point, there is a condition at the nth point. So this means that in total, how many U's are you expecting? You are expecting N plus 1. N was 10, then 11 values here, right? So the order of this matrix is 9 cross 11, and here you have 11 cross 1. So in the answer, you will get 9 cross 1, right? After multiplying these two matrices. And similarly, by substituting the values of N from 1 till N minus 1, from the left hand side, you will get this matrix. Okay, so now students, this thing is in your hand now. Now, another important point, please make a note on your notebook. After the midterm evaluation, we will go to the finite element method, which is very important part of the numerical methods for partial differential equations. So in finite element methods, we always talk about the mass matrix, stiffness matrix, and we usually compose, like if I have got a big matrix, I will write it in with a symbolic, right? Let's say it is capital M or capital S or capital F. So now we are getting ready for those things as well. So what am I going to do now in the next slide? For these two matrices, I will use the small names, right? Short names. So I'm going to call left M and right M. Now I have J plus 1 U vector with J plus 1 entries. So at the J plus 1th time, I will call it uj plus 1. At the jth time, I will call it j. It is very clear. Let me go take you back here. So here you can see j, okay, and here you can see j plus 1, okay. And now the first and the last rows of these vectors. We can always remember that we can always write the matrix as a sum of two matrices. So what have I done here, students? This is very, very important. I have got this thing, u1j plus 1 n minus 1j plus 1. Now it is looking very fine. Now the product is also n minus 1 cross 1. Let's say if n is 10, then the order of this matrix of the product is 9 cross 1, and the order of this matrix is also 9 cross 1. Why? Because now, students, you can see that I have removed the top and the bottom rows, and I have written it in a separate matrix form here. Okay, this is a very, very important step in the derivation of averaged Crank-Nicholson scheme. So now, similarly, from the other side, you will get this vector. We will call it R, and this is nothing but it is straight away depending on the boundary conditions. So in the MATLAB M file, you will see that we will just define the boundary conditions. We will utilize these with the help of the indices, and the R will be used automatically. But when you are writing the numerical scheme here, the Crank-Nicholson scheme here, then remember that we will write the R's here on the right hand side. And now a very important point is that at the temperature at the j plus 1th time is given as the temperature at the jth time times the matrix at the jth point. Now remember, these matrices will be known to you. How? Through lambda, through the tri-diagonal matrices. Okay, these are the tri-diagonal matrices. Through R's are the boundaries. This will be given to you. Next, mj plus 1 inverse. This is the inverse of the matrix M. This was also known to you, and you will find its inverse. Now, inversion is not difficult, but it is time consuming. So let us go to the MATLAB M file and let us demonstrate this M file. So let me Okay, so now what is happening in this M file? Let us go through this M file step by step, and let us solve one question, and then I will give you one question to solve using this MATLAB M file as a third online task. Okay, so and then task name will be Crank-Nicholson averaged task. And when you submit that task, please submit it with email subject, your name, registration number, and task name. Task name is Crank-Nicholson average. Okay, please make a note on your notebook. Sometimes it is difficult for the evaluation when you send me 7, 8 emails or 6 emails and with the same assignment. So it is difficult for me to evaluate. So please be organized. Okay. Now let us talk about this M file, a very nice M file. Now it is a very trivial M file. Now you can see here that the length of the rod is 1 L, final time is 1. Now maximum number of time steps is too much, 2500. Maximum time space steps are only 50. Okay, now what is this? This is delta T, and this is delta X. Now remember that when we select delta T and delta X, we need to satisfy the stability criteria. We will go to the stability criteria after this M file. Okay, now currently let us focus on this M file. And what is happening here, we are going to simplify it. Remember that this B in this formula is alpha. Okay, in this M file. Now what is this loop? This loop is for the initial condition. Okay, let me write here. This is for the, and it is given already, it is a sinusoidal initial condition. Okay, so now ux0 is written here as ui1. Remember, 0 in MATLAB brain is 1, right? For the indices. Right, now let us go to the boundary conditions. Your boundary conditions are zeros here. In this question, the boundaries are 0, 0, starting and ending. Okay, now what will happen next? Now, do you remember before the lockdown, we discussed an MPhil in the classroom where I taught you how to write the tridiagonal matrices. So here I have defined the left and the right tridiagonal matrices. You can see that these are the entries along the diagonals: minus alpha, 2 plus 2 alpha, minus alpha. Right here, plus alpha, 2 minus 2 alpha, as given in the numerical scheme here, right? So now I have defined the matrices. Very easy way is just to substitute these matrices here and evaluate it with the help of a loop. Remember, we will need a loop. Okay, now students, I'm going to write a loop, and then because I know that the boundaries were given to me, so I will start my index from 2 till maximum k. Okay, because one initial condition was given to me. K is the index for time, and then initial condition for given was given to me. So 1, and this is the final time. And here you can see this these indices are for space. 2 is to end means that start one index was given to you, that was the boundary, right? One index was given to you, that was the time. For the time, that was the initial condition. For the space, that was the boundary condition. Okay, now this is nothing but exactly the same numerical scheme, and R's were absorbed here as the any boundary conditions. Okay, now once your numerical scheme is ready, this is your numerical scheme. Now you are going to plot it. How will you plot it? There are two ways. Either you can plot the line plot, or you can plot the surface surface with the help of mesh. X, time, and U is the temperature. Okay, now let us run this M file and let us see what we get. So you can see here that this is the surface, very nice and smooth surface. The reason is that you have got sufficient number of grid points. Delta X was small, delta T was small, so results are very nice. And here you can see very nice graphs at different times. How at T is T index 1, at T index 100, at T index 300, at T index 600. Okay, now students, let us say that we want to change this question, right? We want to change the step sizes, let's say, and we want to see that if I have very coarse grid, let's say I have only 6 in time and only, let's say, 8 in space. Okay, then I am expecting that I will get very bad results, bad numerical results, not very smooth or not very fine graphs. Okay, so let us now run the code and let us see what we get. So here, because you have got an error, why? Because you are asking MATLAB to evaluate at 300, 600. So let us change this command to only to 8. Why? Because you are saying that you have very um, limited number of data points and very big step size. Okay, so now let us again, 8 is bigger. Why is it bigger? Because you can see here that maximum T is 6. Okay, so let us make it 10, and now let us run it. Now students, you can see, can you see now the surface is not that nice as it was before? Yeah, so you can see here the points, and now let me take you to this graph. Now it is not that nice. Yes, and now let us make it more coarse. So I am going to make it 4, 4, and this time I will not forget that now my index is very small. So let's say 1 and 2 only. Okay, so let me run it. Now can you see this time the results are very bad? The reason, can you tell me the reason? The reason is that I have the points located at very very far positions. They are having a big step size. Can you see here, students? Yes, how many points are there? 1, 2, 3, 4, 5, n plus 1, right? Which is not nice. The results are very bad. Step size is very big. Yes, and the temperature, you can see it is not that very clear at all the points. Okay, the surface is not very smooth. So now let us discuss the stability analysis. Okay, and before we go to the stability analysis, I want to give you the homework, the next homework. And remember, the name of the homework is CN average. Okay, now what are you going to do, students? Because you are now familiar with this example, let me take you here. Now what is new here, I guess I have already done it here, but the only difference this time is that you will change the step size 3 times. Please make a note on your notebook during the video. H is 0.25, K is 0.25. So you have the liberty. You can make it H is equal to 0.2, K is equal to 0.1 or anything. So for 3 sets, you will produce 6 graphs. For 1 set, you produce 2 graphs. For 3 sets, you produce 6 graphs. And you will produce a Word document. You will paste your images to the Word document. And for each graph, you will give a title on the Word document that for this graph, I had K is equal to 0.1, H is equal to 0.2, something like that. And then you will tell me, you will talk to me through your assignment. You will tell me which results were the best. Okay, and the answer is given in this video. So the homework is change the step sizes 3 times, produce 6 graphs, transform them to a Word document, send it to me by email. Email subject must be your name, registration number, and CN average must be the email subject. Okay, now let us go to the stability analysis of the averaged Crank-Nicholson scheme. Now it is, because it is the average of explicit and implicit FTCS scheme, this advanced Crank-Nicholson. So we need to talk about stability analysis. Previously for the implicit one, Crank-Nicholson scheme, we didn't talk about the stability analysis, but now we will do. Now for this scheme, the stability analysis is that we will talk about the amplification factor. And if we take the magnitude of this amplification factor, we say that it is true for any delta t, the scheme is unconditionally stable and the second order both in time and space. It is worthy to analyze it more deeply. For that good reason, I have given you the homework, so that side by side you will be able to analyze the results for different step sizes. Now students, what is the amplification factor? The stability analysis for Fourier approach, von Neumann method. Now we have not gone through this in detail, but this is homework. This is not an assignment, but a homework to read from documents pde.pdf in detail about the stability analysis. And remember that why do we need the stability analysis? As we discussed in the classroom, we need the step sizes for which the error will not accumulate. Let us read this sentence. The system is said to be stable if these rounding errors are not magnified at each iteration. Ask the question, if a small error is introduced into the system, in the solution, is it magnified by the numerical method or does it decay away? Decay away means that with the passage of time, the error will grow very small and your numerical result will look exactly like your exact result. So now students, let us go to the basic introduction of the Fourier approach, and this is what we have already done in the classroom, but I would like to go through it again. We learned the separation of variable method in the beginning. So similarly, you can see that U and J, the temperature or the velocity or whatever partial differential equation you are using, according to that you have the function U of space and time. And J, you can decompose it into time and space functions, U of t, E of x. Okay, so now you will substitute it in your numerical scheme or in your partial differential equation and you will end up with this xi. And if the magnitude of this xi is greater than 1, it is unstable. If it is less than 1, it is stable. Okay, now please don't forget to read the handouts that I have provided you, and the Crank-Nicholson averaged M file is given in the pde.pdf. Take the M file from there and solve the question and send it back to me by Saturday 2 p.m. Saturday 2 p.m. Today is Wednesday, so you have 3 good days. And I am preparing your mark sheet, so I will add the marks time to time in that sheet. And please do me a favor, just send me one single M file for one task and with your name, registration number, and the assignment name. Today's assignment name is Crank-Nicholson Average. Okay, and I hope to speak to you soon. Allah Hafiz.